At the start of this summer, meteorologists across the agricultural world made a fairly confident prediction. With a powerful El Niño developing in the Pacific, the Corn Belt and much of the American Midwest were expected to run cooler than normal this season, a forecast built on decades of prior analog years and well-tested seasonal modeling. That is not what happened. Instead, persistent punishing heat settled in and refused to leave, and when scientists went back to figure out exactly why their forecast broke down, they found something genuinely surprising about how this particular jet stream has been behaving. To understand why this forecast failed, you first need to understand a rule that atmospheric scientists have relied on for decades, one that turned out to matter enormously this year. According to a senior atmospheric scientist at Nutrien, if it is summertime, you cannot treat El Niño as the primary driving force behind a region's weather pattern. That sounds counterintuitive, given how much attention El Niño gets every single year, but the reasoning behind it is straightforward. El Niño exerts its influence on global weather largely through the jet stream, and during summer months, the jet stream naturally weakens and retreats far north as it follows the sun's higher angle in the sky. A weaker, more distant jet stream simply has less grip on the atmosphere below it, which means local heat and moisture dynamics typically take over as the dominant factor in day-to-day summer weather, rather than the big picture signal coming from ocean temperatures thousands of miles away in the Pacific. Seasonal forecasters build their outlooks using a method called analog summers, essentially searching through decades of historical records to find previous years where ocean temperatures, jet stream behavior, and other key indicators closely resembled current conditions. By comparing how those past analog years actually played out, forecasters can identify likely temperature and precipitation patterns for the season ahead, refining those early estimates further using long-range climate models and government forecasting resources. It is a genuinely useful method in most years, precisely because it leans on real historical precedent rather than pure model speculation, though its accuracy depends entirely on the current year actually resembling the historical years being used for comparison. That rule has held up reasonably well in past summers, giving forecasters a useful, dependable shortcut for setting expectations before each growing season begins. This year it didn't, and the reason why is exactly what makes this particular El Niño so different from the ones forecasters have studied before. This year's El Niño developed unusually fast, setting records for its pace of intensification. Water temperatures in the official El Niño monitoring zone climbed to just over 2 degrees Celsius above average, higher at this point in the season than every other recent. It began increasing upper-level winds across the tropics and subtropics months earlier than meteorologists typically expect any El Niño influence to show up during summer. In other words, the jet stream never got the chance to properly retreat and go quiet the way it normally does this time of year. Instead, an unusually strong, unusually early atmospheric signal kept interfering with the exact process that seasonal forecasters had built their summer outlook around. Some computer forecast models have gone even further, suggesting this El Niño event could ultimately become the strongest on record dating all the way back to when modern record keeping began in 1950. That is a remarkable statement on its own, but it also underlines exactly why this summer's forecast broke down so decisively. Forecasters were not simply off by a small margin, working from analog summers and historical comparisons that turned out to be reasonably close. They were attempting to forecast a season shaped by an event unfolding faster and more powerfully than any of the historical analogs those forecasts were actually built on. If you're finding this as fascinating as I am, go ahead and hit that like button. Understanding exactly why forecasts succeed or fail is precisely what this channel is here for. Here's where the story gets genuinely strange, though, because that same disrupted jet is above it to maintain its structure. Blow a strong jet stream directly over the top of a developing storm, and that wind spreads the heat energy out and tears apart the storm's vortex before it ever gets the chance to organize. Right now, temperature values across the tropical Atlantic, the Caribbean, and the Gulf are running remarkably high, exactly the kind of warm water that would normally fuel powerful hurricanes, and yet storm systems simply cannot survive long enough in that wind environment to end up running at roughly half of its historical average activity, based entirely on this wind disruption. That represents a fairly dramatic shift from how the season looked earlier in the year. Back in the spring, before El Niño's rapid intensification became fully apparent, some outlooks had suggested a fairly typical hurricane season was possible. Watching that projection collapse toward roughly half of normal activity within the span of just a few months is itself a striking demonstration of how quickly this event has been reshaping expectations across completely different corners of the weather system simultaneously. So if the jet stream was strong enough to shred hurricanes in the tropics, why didn't that same strength also deliver the cooler, more active summer pattern the Midwest was originally promised? This is exactly the paradox that caught forecasters off guard. And the answer comes down to where specifically, that disrupted energy actually went. The stronger winds associated with this early El Niño signal were concentrated over the tropics and subtropics, the regions that directly influence hurricane formation. But because the broader mid-latitude jet stream still followed its normal seasonal retreat further north, the cooling and storminess that typically rides along the jet stream's boundary simply wasn't positioned to reach the Corn Belt and eastern Midwest the way analogy. Summers from past El Niño years had suggested it would. The atmosphere effectively split its behavior, disrupting the tropics dramatically while leaving the mid-latitudes to bake under increasingly localized stagnant heat. Two regions of the same planet responding to the exact same underlying event in almost entirely opposite ways. Make sure you're subscribed to this channel because we're going to keep tracking exactly how this pattern develops as we move through the rest of hurricane season. This localized stagnation matters enormously because it explains why heat this summer has felt so relentless in specific regions rather than simply following the broader El Niño script forecasters expected. When jet stream activity weakens over a particular region, that area effectively gets cut loose from the larger atmospheric currents that would otherwise bring in cooler air or trigger storm systems, day after day, with nothing forcing it to move on. That is precisely the mechanism behind several of the summer's most intense heat events, persistent ridges of high pressure locking in place for a week or more at a time, because the usual atmospheric traffic that would normally break up that pattern simply was not there to do the job. This is exactly the dynamic the nutrient atmospheric scientist was describing when he emphasized that summer weather tends to run on more localized rules than winter weather does. In winter, a strong, fast-moving jet stream dominates the entire hemisphere. Outcomes. In summer, with that same jet stream retreated and weakened, weather becomes far more a product of what is happening on the ground immediately below it. Soil moisture, regional humidity, and whatever high-pressure system happens to already be sitting nearby. This year's early, aggressive El Niño essentially tried to impose winter-style influence onto a summer atmosphere that was not structurally set up to transmit that influence the same way, producing genuinely unpredictable results in the process. Forecasters studying this pattern have been careful to point out that producers and planners often focus heavily on these large-scale climate drivers like El Niño, treating them as the single dominant explanation for an entire season's weather. But this summer has been a clear reminder that localized interactions frequently dictate the actual outcome on the ground, sometimes overriding what the bigger picture climate signal would otherwise suggest. Knowing that El Niño is developing tells you something important about the broader system, but it does not guarantee you know exactly how, when, or where that influence will actually show up during the summer months specifically, especially when the event itself is developing at a pace nobody has quite seen before. For farmers and agricultural planners specifically, this distinction carries real financial consequences. Planting decisions, irrigation planning, and crop insurance calculations often lean heavily on seasonal outlooks built months in advance and a forecast promising a cooler corn belt that instead delivers persistent, punishing heat can meaningfully affect yield expectations across an entire growing season. That is precisely why atmospheric scientists working in the agricultural sector have been so vocal this year about explaining not just what the forecast got wrong, but why it got it wrong, since understanding the underlying mechanism helps producers interpret next year's outlook with a more appropriately calibrated level of confidence. This is precisely why meteorologists are treating this summer as a genuinely important case study, not just for understanding 2026 specifically, but for refining how forecasters build seasonal outlooks going forward. An El Niño event developing this early and this aggressively essentially broke the normal seasonal separation scientists have relied on, where winter forecasts lean heavily on ENSO signals, while summer forecasts lean more heavily on local and regional patterns. When an event intensifies fast enough to bleed its influence into summer months that would typically be dominated by local dynamics. Instead, the old rules of thumb that seasonal forecasters have used for decades stop applying cleanly, and meteorologists are left rebuilding their expectations in real time as the season unfolds around them, adjusting each new outlook against a moving target rather than a settled, well-understood pattern. So what happens from here? With El Niño still intensifying and expected to persist through at least the end of the year, the same disrupted jet stream dynamics that caught forecasters off guard this summer are likely to keep influencing conditions well into autumn and winter, when El Niño's classic, well-understood influence on the jet stream traditionally becomes most dominant anyway. The open question meteorologists are now watching closely is whether this summer's unusual early disruption was simply a preview of an even more powerful reorganization still to come, or a temporary quirk from an event still finding its footing. There is a reasonable argument for both possibilities. On one hand, once autumn arrives, and the jet stream naturally strengthens and shifts southward again, as part of its normal seasonal cycle, El Niño's influence should, in theory, finally align with the structural conditions that typically allow it to dominate a season's weather pattern cleanly, potentially producing the kind of textbook winter outcomes forecasters have successfully predicted in past events. On the other hand, if this El Niño continues intensifying at the record pace it has shown all year, it may simply keep finding new ways to disrupt whatever seasonal assumptions forecasters build their outlooks around next, the same way it already disrupted this past summer's Corn Belt forecast so decisively. Either way, this summer has already demonstrated something meteorologists will be studying for a long time, that even one of the most well-understood climate patterns in modern forecasting can still break the rulebook when it arrives fast enough, strong enough, and early enough to catch the entire system off guard.